Welcome, dear students. Now we discuss about MCQ 2022 Metric Spaces and Complex Analysis, paper CC-13, semester 6, B.Sc Honours in Mathematics. (2022) paper CC-13 Metric Space and Complex Analysis. Question 1a. Which one of the following is not a metric on R set of all real numbers? Correct option is 2. Now, from the identity condition of metric space Rd, R is the set of all real numbers and D is the metric defined on R. We have dxy equal to 0 if and only if x equal to y. Now, 1 comma minus 1 belongs to R. So, d1 comma minus 1 is equal to 0, but 1 not equal to minus 1. And note that this metric dxy equal to mod of x square minus y square is not a metric, but D is a pseudometric on R. This matrix defined into pseudometric and which satisfies the following conditions is xy belongs to R and x equal to y implies dxy equal to 0. Number 2, dxy greater than equal to 0 for all xy belongs to R. Number 3, dxy equal to dyx for all xy belongs to R. Number 4, dxz less than equal to dxy plus dyz for all xyz belongs to R. Next question 1b. Let xd be a metric space and A be a subset of X. Choose the correct statement. Option 1. Let xd be a metric space and A and B subset of X. A point X belongs to A is said to be an interior point of A if there exists an R greater than 0 such that X belongs to SRX. This SRX is an open ball with center at X and radius R, positive radius, R is positive. This open ball, open sphere, is a subset of A. The set of all interior points of A denoted by A naught is called interior of A. Now we know this A is a subset of B implies A naught is a subset of B naught. Now A intersection B is a subset of A intersection B is a subset of B. Hence, by this property 1, A intersection B the whole naught is a subset of A naught and A intersection B the whole naught is a subset of B naught. Hence, we get A intersection B the whole naught is a subset of A naught intersection B naught. Let X belongs to A naught intersection B naught be any element. Then X belongs to A naught and X belongs to B naught. Then there exists R1 greater than 0 and R2 greater than 0. We get two open spheres SR1X and SR2X such that X belongs to SR1X. This is a subset of A and X belongs to SR2X, a subset of B. This centered at X and radius R1. Here center is at the point X and radius R2. And let R is the minimum of R1, R2. Then this open sphere SRX is a subset of SR1X and SRX is a subset of SR2X. Therefore, X belongs to SRX is a subset of SR1X intersection SR2X and this is a subset of A intersection B by 3. This implies X belongs to A intersection B whole lot. That is the definition of this interior uh, point, interior point of this. Thus, X belongs to A naught intersection B naught implies X belongs to A intersection B whole lot. Hence, A naught intersection B naught is a subset of A intersection B whole lot. Equation 4. And combining equation 2 and equation 4 equality holds. So A intersection B whole not equal to A naught intersection B naught. Next question 1c. Let X D1 and Y D2 be two metric spaces and F maps X to Y be a continuous mapping. Then correct option is this: F inverse F is closed in X whenever F is closed in Y. Let X D1 and Y D2 be two metric spaces and let F maps X to Y be a continuous mapping on X and F is closed in Y. Then Y minus F is open in Y because F is closed in Y. So F inverse Y minus F is also open in X. But F inverse Y minus F equal to X minus F inverse F. So X minus F inverse F is open in X. That is, X inverse F is closed in X. Hence the result. Note that open sets are complements of closed sets and vice versa. Number 2, F is continuous if and only if F inverse G is open in X whenever G is open in Y. Number 3, F inverse capital F is the complement of F inverse Y minus capital F in X, that is F inverse Y minus capital F equal to X minus F inverse capital F. Next question 1D. Let A is the set of all those 1 by m plus 1 by n such that n belongs to the set of all natural numbers capital N. Union the singleton set 0. Then A is a subspace of the real line R. Is correct option is 3, compact and complete. A is the set. Clearly 0 less than equal to x less than equal to 2 for all x belongs to capital A. Then the set A is bounded subset of the set of all real numbers. The set of all real numbers, these are the set of all limit points of A, that is the derived set of A, that is A dash, this equal to singleton set 0, union the set of all those 1 by n such that n belongs to set of all natural numbers n. And then A dash set of all limit points is a subset of A. Then A is closed. Hence, by Heinable-Borel theorem for real number, every closed and bounded subset of R is compact. Hence, A is a compact set. Also, we know that a compact metric space must be complete. Hence, A is a compact and complete metric space. Complete subspace here are. Next question E. Let R du denotes the usual metric space of the real number R, set of real numbers, and R d star denotes the discrete metric space of R. Then which of the following statement is true? Correct option is true. Every du open set is d star open. Let R du be usual metric space of the set of real numbers R. Then du xy is the modulus value of x minus y. X comma y belongs to R. The usual metric, this du. On the real line R, the open ball is Rx, center at x with radius R, is the open interval x minus R, comma x plus R, and let R disturb the discrete metric space of R, then disturb xy equal to 1 when x not equal to y, and this equal to 0 when x equal to y. Xy belongs to R. Then the open ball SRX is the singleton set X when 0 less than R less than equal to 1, and this SRX equals to the set of all real numbers R when R is greater than 1 for this R disturbed metric space. Now we know that this AB open interval is a basic open set in the usual metric space R du, and all subsets of R, and so in particular AB open interval, are also open set in the discrete metric space R disturbed. Hence the result 2 is correct. Next, from complex analysis, question F. Let fz equal to modulus of z by real of z if real z not equal to 0, and fz equal to 0 if real z equal to 0. Then correct option, f is not continuous at z equal to 0. Let z is equal to x plus iy, where x and y are real numbers, and I square equal to minus 1. Then real z equal to x, and modulus of z is equal to root over of x square plus y square. Now limit z tends to 0 fz, this is equal to limit z tends to 0. So obviously z not equal to 0, so we can take the value of fz is this mod of fz by real z. This is equal to limit x tends to 0, y tends to 0, this root over of x square plus y square divided by x. Let z tends to 0 along the curve y equal to mx. Then we put y equal to mx here, so limit becomes root over of 1 plus m square, which gives different values of for different m. So the limit distance to the fz does not exist, and consequently fz is not continuous at z is equal to 0. Next question G. The radius of convergence of the power series, this n root 2 plus I whole divided by 1 plus 2in whole bracket z to the power n, correct option is 1. Let an equal to this nth term. Then modulus of an equal to this, multiplying numerator and denominator by 1 minus 2in, and after simplifying we get this modulus of this plus I into this. So this modulus of x plus iy, this is equal to x square plus y square, root over of x square plus y square. So after simplifying we get this 1 by 4, 1 plus 4n square root over of 8 into the power 4 plus 6n square plus 1. Next, the modulus of a n plus 1 term. A n plus 1 term is this, so put here n plus 1 in place of n. And the radius of convergence R is given by limit n tends to infinity modulus of an by an plus 1. So an, value of an is this, and value of an plus 1 modulus of this, and this, dividing numerator by n square, and this n to the power 4. Sorry, it is n square because in the root this n to the power 4. So here n square and here n square, and denominator also here by n square, denominator here by n square. So after simplifying we get this, since limit n tends to infinity, so 1 by n square equal to 0. So after cancellation this we get this limit is 1. Next question H. the Mobius transformation which maps Z1 equal to 0, Z2 equal to minus I, Z3 equal to 1 onto W spaces W1 equal to I, W2 equal to 1, W3 equal to 0 respectively is given by correct option 1. W equal to minus I Z plus 1 by Z minus 1. Here in the Z plane, this 0 minus 1 y minus I minus 1 and W is the I 1 0 for Z0 Wi. The required bilinear or Mobius transformation is given by W minus W1 into W2 minus W3 whole divided by W1 minus W2, W3 minus W equal to Z minus Z1 into Z2 minus Z3 whole divided by Z1 minus Z2 into Z3 minus Z. You can remember by this diagram. So W minus W1, this is W0, W1. Next one gap, this W2 minus W3, W2 minus W3 whole divided by W1 minus W2, W1 minus W2 after one gap, W3 minus W, W3 minus W. Similarly for J. Substituting these values for Z and W, we get this, and after simplification, we get this W equal to I into 1 minus Z by 1, 1 plus Z by 1 minus Z, that is W equal to minus I Z plus 1 by Z minus 1. Z plus 1 by Z minus 1. Next question, I. Control integration over C Z plus 4 by Z square plus 2Z plus 5 dz, where C is the circle, modulus of Z plus 1 equal to 1. Correct option is 3. Now, this denominator Z square plus 2Z plus 5, so after simplification, 1 by Z square plus 2Z plus 5 equal to 1 by Z plus 1 whole square minus 2 whole square. So we can write this 1 by 4i 1 by Z plus I minus 2i minus 1 by Z plus 1 plus 2i. Now modulus of Z plus 1 equal to 1, that is modulus of Z minus 1 plus I into 0 equal to 1. This represents a circle C with center minus 1 comma I 0 and radius this 1. So minus 1 0, that is minus 1 0, this point minus 1 0 center and radius is 1, so this is a circle, represents a circle. And this point, this numerator, this for this numerator Z is equal to minus 1 plus 2i and Z is equal to minus 1 minus 2i. Now for this denominator, where denominator equal to 0, so at these points denominator is 0. Now we check whether these points lie within the circle or not. For this, modulus of Z plus 1 equal to, put the value of Z minus 1 plus 2i plus 1, cancel this, so modulus of 2i is equal to 2, obviously greater than 1. Then this minus 1 plus 2i is outside the circle, and Z plus 1 for this Z minus 1 minus 2i, this 2 also outside the circle. So this Z equal to this, so numerator 0, denominator equal to 0 outside the circle C. By Cauchy's theorem, if fz is analytic and f dash z is continuous inside and on a simply closed curve C, then integration over C fz equal to 0. Hence, fz equal to z plus 4 by z square plus 2z plus 5. We can write z plus 4 by 4i into 1 by z plus 1 minus 2i minus 1 by z plus 1 plus 2i, because we write 1 by this equal to this. So clearly, if z is analytic inside and on C, And as z equal to -1 plus 2i and z equal to -1 minus 2i both lie outside of the circle C. Hence, by Cauchy theorem, integration over C f z is equal to 0. Next question, question J, last MCQ. 1 by 2 pi I integration C z square plus 5 by z minus 3 dz, where C is the modulus of z equal to 4. And correct option is 14. 4. Correct option is 4. Answer 14. Now, Cauchy's integral formula states that if fz is analytic within and on a simply closed curve C and A is any point inside C, then fa equal to 1 by twice pi I integration over C fz dz by z minus A. Here, modulus of z equal to 4 represents a circle C with center at 0, 0 and radius 4. So here, denominator is z minus 3. So we check whether this z minus 3, that is whether this denominator equal to 0 for value z equal to 3. So z equal to 3, this z equal to 3 lies inside the circle C, because if you put z equal to 3 here, so 3 is less than 4. So inside the circle z equal to 3. So by Cauchy's integral formula, this A is inside point C, then formula f equal to 1 by twice pi I. So f equal to 1 by twice pi I fz by z minus 3 dz. Here fz is equal to z square plus 5. So fa, that is f3, equal to 14. So correct answer is 14. Thank you for watching this.